This is Introduction to VLSI Design class. And today we'll talk about three subjects. The first one is the scaling and economics. And after we finish it, we will talk about the packaging, the power, and the clock. And we will finish with the input and output. Each one of them is a short talk. So we combine all of these three together. We will start with the scaling and the economics. So we will see the scaling in the transistor and the interconnect and some of the challenges there. And we will talk also about the economics. The only constant in VLSI is constant change, actually in everything, including VLSI. The feature size, as you remember when we talked at the beginning of this class, shrinks by 30% every 2 to 3 years. And if you compare two or take the ratio between two consecutive generations, the scale factor S is going to be equal to the square root of 2. Now, we have Dinar scaling. It was introduced 1974. And basically, he says that with every generation, the length, the width, the gate oxide thickness, the VDD, and the V threshold, all of these parameters scales down by S. When we say 1 over S, this means that it is a scaling down. The doping, or NA, is scaling up by S. Now, for other parameters, for example, like beta, we know beta is W divided by L multiplied by thickness oxide. This is the sensitivity of the beta, meaning we will substitute whatever scaling for each parameter. So for W, it's actually 1 over S. And for L, it's also 1 over S times the thickness oxide. Again, it is 1 over S. So you can cross this one with this one, and you will end up with S. This is why beta is scaling up by S. And you can do the same for the rest of the parameter, like the ion, the resistance, the capacitance, tau, and so on. So all of the parameters affected by their own sensitivity, or how do you calculate them. As an observation, the gate capacitance per micron is nearly independent of the process, but the on resistance times micron improves with the process. How is this? Now we know the width is scaling down 1 over S. Similarly, for the capacitance is 1 over S. The capacitance is, we mentioned that here, and it's 1 over S. So it's scaling down by S. The resistance is remaining the same because this is what we have here. The resistance, it's V divided by I. And we know that the V is scaled down by S, and the I is also scaled down by S. So the resistance remains constant, which is equal to 1. From that, you can get the capacitance per micron, where it is going to be 1 over S divided by 1 over S, which will be equal to 1. So this is why we say that it is independent of the process. Resistance time microns, time the size, is actually 1 times 1 over S, this 1 over S, which equals to 1 over S, which is actually improves. It scales down at every generation. So the gas gets faster with scaling, and that's good. The dynamic power goes down with the scaling, and this is also good, but the current density goes up with the scaling, and that's that. Now, let's have an example to prove this point. If we say that the gate capacitance is typically about 1 femtofarad per micrometer, the typical fan out of 4, and remember we said that fan out of 4 is equal to 5 tau, which is actually 5 times 3 RC. So the typical fan out of 4 inverter delay for a process of a feature size F, and this you have to make the distinction between this F and femtofarad, so don't be confused. In nanometer is about 0.5 F times or 0.5 F picosecond. Estimate the on resistance. So we're talking about the resistance that I just mentioned that we are interested on this point here of a unit transistor where the width is 4 and the length is 2 lambda. So as I said, the fan out of 4 is 5 tau, which will be 15 RC. Since 15 RC is equal to 0.5 F given by this, then the RC is actually 0.5 times F divided by 50, because we said here the fan out of 4 inverter. So we divide by 50. Now the RC from this is equal to F divided by 30 picosecond per nanometer. Now let's investigate. If W is 4 lambda given by this, meaning it's 4 times F divided by 2, recalling that lambda is equal to the feature size divided by 2, which will in turn be equal to 2F. Then the C, which will equal to the C per micron times W. Now, the C per micron is given to us as 1 femtofarad per micrometer. So it is 1 times the W that we just got, which is 2F. 2 feature size. Now the resistance, to get the resistance, we actually, since we have the capacitance now, we will just substitute the capacitance value. So it is F divided by 30 picosecond per nanometer divided by C. And now we divide by C. And notice now that we take out the F with the F. That's the important part here. And the ending result of the resistance is 16.6 kilo. Here we're saying the unit resistance is roughly independent of F because it was cancelled. Then the on resistance times micron improves with the process. And that's the idea. Now, the real scaling of what's going on in the recent generations. Now, the thickness oxide and also the VDD, even the V threshold, they are not scaling well anymore. So we are stuck there. So in the thickness oxide, the scaling has slowed since the 65 nanometer, limited by many things like the gate tunneling current. And now the gates, even they are only 4 atomic layers thick. And you have high K dielectrics that have helped continue scaling of effective oxide thickness. The VDD scaling has slowed down also since 65 nanometer. The SRAM cell stability at low voltage is challenging now. Now, the Dennard scaling predicts cost, speed, power, all improves. But that was since the beginning of Moore's law up to the 65 nanometer. Now, below 65 nanometer, some designers find they must choose just 2 of the 3, cost, speed, and power. So let's go back to the table to understand what is the recent complications. Now, the V threshold actually doesn't scale anymore after the 65 nanometer. Let's say that it's slowing down, and currently, recently, as we are reaching 1 nanometer, the V threshold is not scaling down anymore, so it's equal to 1. The VDD doesn't scale down to, is equal to 1. And there are so many other effects. And because of this, one of the things that is really challenging nowadays is the switching power density or the power in general. Prior to the 65 nanometer, it was actually constant, and that's amazing. So each time we are gaining performance, we are gaining better performance indicated by the clock frequency. Every time we are getting, it's scaling up with constant power consumption. However, because of this and other factors, the power density is actually scaling up, which is bad news. And because of this, we cannot increase the frequency anymore. And that's basically the main reason we are moving from increasing the clock speed of a single core to the idea of multi-core processors. So now we will see the interconnect scaling. Again, we have the width, spacing, thickness, and height scaling down. The die size is scaling with another factor, which is DC. You can see that the other factors here, or the other parameters, with their own sensitivity based on the basic parameters, they have certain scale. For the interconnect delay, we have the length, the unrepeated wire RC delay, the repeated wire delay, and the energy pair bit with their own sensitivity here. The length L is scaling down. We have the local parameters or the local scaling, and we have the global scaling of the wires with their own parameters. So scaling is very important. This sheet can help predict what to do in the next generation. Some observation, main observation here is the capacitance per micron is remaining constant, which is about 0.2 femtofarad per micrometer. And that's actually the assumption that we said when we talked about the interconnect. It's roughly the fifth of the gate capacitance if the gate capacitance is 1 femtofarad per micrometer. The local wires are getting faster, not quite tracking transistor improvements, but not a major problem. And that's actually good news. The global wires are getting slower. And that's the kind of bad news here. So no longer possible to cross the chip in one cycle. You need more than one. Now, here at this point, we finish the scaling part. We will move the power part. We talked about the power, and we say that the components are the dynamic power and the static power. For the dynamic power, until VP in 2001, he said, if scaling continue at present pace, by 2005, he was making this speculation at 2000. So if he said if scaling continue at the present pace, by 2005, high-speed processor would have power density of nuclear reactor, and by 2010, a rocket nozzle, and by 2015, the surface of the sun, which is impossible to have this on Earth. So that's basically also another reason we moved to the multi-cores, or we found other solution. So business as usual will not work in the future. That's what he said. So because of this and many other factors, attentions to power is increasing. You can also look at this figure with years and power density. You can see here, at that time when 2001 happens, we were reaching at this point, and it's moving up exponentially. And by 2010, we are reaching the surface, the sun surface. For the static power, the VDD decreases. This saves the dynamic power, protecting gate oxide and short channels, and there's no point in high value because of the velocity saturation. The V threshold must decrease to maintain the device performance, but this causes exponential increase in the off leakage. It's actually a major future challenge, as we said. Now, if you compare the dynamic to the static power, the static power currently in current generations are the dominant part, are the one that you need to work with more than the dynamic power consumption. So most of the power consumption is coming from static power nowadays. This is a sketch where you can see that this is actually more published this in 2003. From 1960 up to 2010, this is the years, and he's calculating the power. In the dynamic, it's going with this slope. The static is actually catching up pretty quickly. So the idea here is that they will cross at a certain point, and after this, the static becomes the dominant part in the total power more there, the dynamic, and this is what happens nowadays. The physical limits, that's actually the main reason when you look at it, frankly. Will Moore's law run out of steam? We can't build transistors smaller than an atom. So the feature size is going down and down as new generations uh, uh, is invented, but we can't get smaller than an atom. We will reach the physical limits. Many reasons have been predicted for the end of scaling, like the dynamic power, the subthreshold leakage, the short channel effects, the fabricating cost, the electromigration, the interconnect delay. Every time now we are moving to a new generation, it comes with its own troubles. And this is actually the rumors of demise. Uh, some also researchers have been exaggerated to even more than that. And now we finish the power part, and we will go to the economics. In the VLSI economics, the selling price of the S total is equal to the cost price, or sorry, the cost, the total cost, divided by 1 minus M, where M is the profit margin. The C total, this cost, comes from many sources, like the recurring cost, the fixed cost, and the non-recurring engineering cost. The NRE could be from engineering costs, depending on the size of the design team, including benefits, training, computers, the CAD tools, like these examples. Also, the prototype manufacturing, the mass cost $5 million in the 45 nanometer process. The test fixtures and package tooling as well, it has their own cost. And from all of this, you have the total cost. And we talked about in the beginning, I think the first video, we talked about how to calculate the cost, and now we are like moving to the price, and it's a very simple equation. You just calculate your profit margin, and it's related actually to other business courses more than the VLSI course. Now let's talk about the recurring cost, which is this one. The fabrication, we have the wafer cost. In the fabrication, we have the wafer cost. It would, or the recurring cost would be the wafer cost divided by the dice per wafer times the yield. Now the wafer cost is $500 to $3,000. The dice per wafer, or what we call N, is equal to pi times this equation where it's R squared divided by A, where R is it's related to the diameter of the wafer, and A is the area of the die, the squares here that you can see in this wafer. So the yield, or Y, is equal to E to the power of minus AD. This is actually a Poisson model, or simply the Y, the yield, will be equal to M in the that is good divided by N that is bad. And N being this, you can get it by applying this equation where it represents the dice per wafer. This is an example. This is the wafer. We have a certain wafer where you have it has its own diameter, or we fixed the diameter in these three experiments. And the first one, we said that the die size is 4 millimeter times 4 millimeter. In the second, it's 20 millimeter times 20 millimeter. And in the third, it's 10 millimeter times 10 millimeters. Now, the yellow ones, or the yellow squares, are the bad dice, or the defect dice that we need to throw away. Since you have bigger die size here, now you can see that the good is only 10 and the bad is 18 out of 28, and the yield is 35.7%. And this one, since we have a smaller die size, now we have more good than the bad. The good is 103 and the bad is 33, and the total of a total of 136, which will represent a yield of 75%. If you get even smaller die size, and this is the recommended one, the good is 620 and the bad is 38 out of 658. And the yield here is a whopping 94% compared to only 35 if you use a bigger die size. So that's a good or best practice. And if you want to increase the yield, meaning that you will reduce the recurring cost, you should have a smaller die size compared to the other. Now we will move to the other subject, which is the packaging, the power and the clock. For the packaging, there are many package sizes. Usually they are either through hole or surface mount. And we talked a little bit about this when we finished the testing video or the design for testability. So as you can see, for example, this one, this one, this one, this one, and this one, and also this one and this one, they are all through hole. For this one, they are clearly a service. They are not actually the service mount is a BGA. It's a ball grid array. But we also gave examples for the surface mounts before. I'm not sure about this one because it's not that clear, but it's one or the other, either a through hole or a surface mount. So the packagings have different packaging. These are some of the names. This is called PLCC. This is called DIP. This is called DIP. This is called the PGA or the PGA, the QFP, and so on. The chip to package bond. Traditionally, the chip is surrounded by pad frame. The metal pad on 100 to 200 micrometer pitch. And you have a gold bond. So now here you have the die and the bond wires. Those bond wires are actually sometimes they are gold. They are fabricated using gold. So you have gold bond wires attached to the pads where you have here a lead frame and then connected using this gold bond wires to the rest of the circuit. Basically to a metal pad there that is connected later into the circuit. And you also have a heat spreader right there. This heat spreader helps cooling down the chip. And the rest of the frame of the chip. So as we said, you have the metal pad. They will be here, and we will talk about the pad when we reach to the input and output. And you have golden wires or the gold bond wires here. And then you have the lead frame connected to the outside pin. Also, you have a heat spreader. Now for the heat dissipation, 60-watt light bulb has a surface area of 120 centimeters square. Now in our case, like for example, an titanium 2 die, it dissipates 130 watt, which is almost double this amount. It's actually more than double this amount over 4 centimeter square only. So the chips have enormous power density. Cooling is a serious challenge. No. So package spread heat to larger surface area. So you need to dissipate the heat. Even the spreader is not enough. The heat spreader here is not enough. You need sometimes on top of that, on top of the chip, if it's a processor, you need a heat sink, and you need cooling methodology. Currently, maybe the fans are not enough. A single fan is not enough. Maybe multiple fans, or even a liquid cooling. So you have the heat sink, as we said, that may increase the surface area further. The fans increase the airflow, and you have also the liquid cooling. And this is used in extreme cases because it costs a lot of money. This is an example. Your chip has a heat sink with a thermal resistance to the package of 4 degrees centigrade per W or per watt. The resistance from the chip to package is 1 degree centigrade per watt. The system box ambient temperature may reach 55 degrees centigrade. The chip temperature must not exceed 100 degrees centigrade or the boiling temperature. So what's the maximum chip power dissipation? To calculate this, we can have to find the ratio, which is 100 minus 55, this 100 minus 55, divided by 4 degrees centigrade per watt, divided by for the plus 1 degree uh, centigrade per watt. Since this is the resistance from the chip to the package, you add those two together and you get 9 watts. This will be the maximum chip power dissipation, which is 9 watts. Now, for the power distribution, the power distribution network function carry the current from pads to the transistor on chip. It should maintain this stable voltage with low noise, provide average and peak power demands, also provide current return paths for signal, avoid the electromigration and self-heating wear out, also consume little chip area and wire, and it should be easy to play with. Now, here is an example for the IR drop. If you have a chip that draws 24 watts from 1.2 volt supply, the power supply impedance is 5 milli ohm. What is the IR drop? So that's an easy question. Actually, to find the IDD is 24 watts divided by the voltage to get the how much current you have, because you know that the power is equal to VI. And the IR drop now is 20 ampere, the one that we just got, times 5 milli ohm, which will be 100 millivolts. That's the IR drop. Now, to get the L or the inductance in Henry times the derivative of the current over time noise, here's an example. If a 1.2 volt chip switches from an idle mode, consumes 5 watts to a full power mode, which consumes 53 watts. So that's in idle and that's in the full normal mode, let me say, or the full power mode. The transition takes 10 clock cycles at 1 gigahertz. The supply inductance is 0.1 nanohenry, that's the value of L. What is the L times the I, or the L times the derivative of the current over some times? This is called a droop as well. So he wants to find this value. We get the delta I and the delta T. The delta is the I of the difference in the current is 53 minus 5 watts divided by the voltage, and you get it as 40 ampere. Now the delta T, you have 10 cycles times 1 nanosecond, since you have 1 gigahertz frequency per cycle, and that will be 10 nanosecond. So now you plug in the values. L is 0.1 nanohenry. The di over dt, you just divide those two together, and you get 0.4 volt. 0.4 volt. And notice that we have the inductance. Since the beginning of the class up to this point, we never mentioned the inductance. We mentioned it as a definition, but we didn't use it. We have to worry about the inductance when we're talking about the package. Now for the energy scavenging, the energy scavenging, The ultra-low power system can scavenge their energy from environment rather than needing batteries. Some of them, like through the solar calculators or through solar cell, like the ones in the solar calculators, or antenna, like the RFID tags. Also, for the tire pressure monitors powered by the vibrational energy of tires. Um, there are thin films, micro batteries deposited on the chip that can store energy for times of peak demand as well. So now we are trying to find energy sources wherever we can. Now moving to the clock. We need to distribute the clock throughout the whole chip. Wherever the clock is needed, we have to supply it. So on a small chip, the clock distribution network is just a wire and possibly an inverter for the clock. On practical chips, the RC delay of the wire resistance and gate load is very long. Now, there are variations in this delay that cause clock to get to a different elements at different times, and we don't want this. And we talked about it, and we named it the clock skew. So you want the clock to be present everywhere in the chip at the same moment. However, you're always going to find certain skew and you account for it. And especially we talk about this point when we talk about the sequential circuit design. We still need to distribute the clock efficiently. So most chips use repeaters to buffer the clock and equalize the delay. It reduces but doesn't eliminate the skew. What are the solutions? We can reduce the clock skew, carefully clock distribute the network design, and that's what we are going to do. Plenty of metal wiring resources. We analyze the clock skew, only budget actual, not worst case skews. It's local versus global skew budgets. And or the other method is tolerating the clock skew. Choose circuit structure insensitive to skew. For example, clocking methodology, we move to the two-phase clocking to get rid of the skew. However, we still need to distribute the clock or do the clock distribution network. And this is what we are going to talk about next. So we have a clock distribution network. There are many methods. The famous ones are the grids, the H-tree, or a hybrid of both ideas. So we will discuss the grids and the H-tree. So this is the alpha clock grid for the alpha version, this version, and moving to the newer version and moving the even newest version. So in this version, we have this horizontal line throughout the whole design. And within this horizontal line, what you do or what you see below it is what's here in the block. So if we have a cross section of this blue line, you will find this where you have inverters, like you see the hierarchy here. We have the inverters here. So the clock or the original clock source will come from this side, and it will be distributed through this network until it touch these points here. And from these points, it goes to the grid, the clock grid. And from the clock grid, whatever system needs the clock, it can get it from the grid to the system. So if there is a circuit or a gate here, it will get it from the grid just on top of it. And the newer version, we have two of them. In the newest one, we have like a more complex grid where you have the clock generated from here after having the PLL, which boosts the frequency. It goes through this line or this wire up to this point. Notice that we have inverters. And this is actually, we talked about this point in wires, and also when we talked about the logical effort. Instead of having a long wire, you are breaking this long wire with inverters to have efficient results in terms of heating. Now you have it in this point, you want to distribute it through the systems that you have here. You have 4 cores, 4 subsystems. So this way you distribute it here, like with these 4 inverters. And you have the connections. Notice that we want to distribute such that the clock will reach to these eyes at the same time. So the symmetry is always there. So you have inverter here, you have inverter here, and you have inverter here, and inverter here. And now from this inverter, it goes to the edges. You see the blue rectangular here. Each one of them is actually, if you have a cross section, it will be like this, an inverter followed by inverter, and then it goes to the clock grid. That's the idea. Now, if you try to see the chip horizontal axis versus the chip horizontal axis, meaning the dimension, and you try to measure the skew, you can see it using this idea. The skew is the variation in skew is a lot. If you have these two, since you have these 2 lines here, you can see the effect on that. So add the line just below the lines, the skew as minimum. And if you are getting away from it or at the corners here, the skew is a little bit higher. Now using this design, you can see that the skew is peaking at the center of these designs since you moved the blue squares to the edges. That's the grid and how we distribute the clock using the grid idea. For the other idea, which is the H tree, it's a fractal structure. It gets the clock arbitrarily close to any points, match delay along all the paths. The delay variation causes a little bit of skew. A and B might see big skew if you have A here and B here. So you have the source from there and look at them as like layers on top of each other to understand them better. So you have the clock coming from the top or the top layer, and it's distributed in 2 paths. And you can see the H letter. This is why we call them H trees. And once it's distributed here and here, you again do the H again here. And then you go to the even lower level, and you have the H again. This way you distribute it fairly to these points at the same time. This, 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 and this, and so on. However, as we stated here, A and B might see big skew. This A and this B that have that goes to different paths. So another idea is using a hybrid networks. You use the H tree to distribute the clock to many points, and then you tie these points together with the grid. And as example, IBM Power 4 or Power PC, the H tree drives 16 to 64 sector buffers, and the buffers drive total of 1024 points, and all points shorted together with the grid. And at this point, we will move to the last part, which is the input and output. In the input and outputs, we are talking about the external points of the chip. Let me go back so you understand where are we. When we talked here about the packaging, we will talk about the pads that are here. These pads could be input, meaning that you have an input from here all the way to this pad, or it could be output. It could be like some calculation in the circuit to the pad, and from the pad going outside to the bank. So the input and output system function communicates between the chip and the external world, derives large capacitance of the chip. It operates at a compatible voltage level. It provides adequate bandwidth. It limits slew rates to control the DI to D or the derivative of the current over time noise, the one that I just give you examples on. But protect the chip against electrostatic discharge or the ESD. It uses small number of pins, which lower the costs if you have pads, input and output. So the bad types, we have the VDD in the ground. You have output, input, and the bidirectional, and also analog bad. So we'll discuss each one of them, the output, the input, and the bidirectional, and the analogs to see what's going on with the paths and how this is connected to your design after you finish your design. So the output path, like this one, the one that you see here, derives large off-chip loads, like 2 to 50 picofarad, with suitable rise and fall times, and requires chain of successive larger buffers. The guard rings, you have guard rings, and we talked about the guard rings in the previous video. The guard rings are used to protect against the latch-up hard error. The noise below the ground injects charge into the substrate and the large inmost output transistor, the P plus inner guard ring, and you have N plus outer guard ring in the inward. So you can see the ring over here, this ring that guards the N plus or the N plus outer guard ring, and you have P plus inner guard ring, which is this one, and then you have the output pad. Now for the input pad, we worry about the level conversion, higher or lower off-chip voltage, and may need thick oxide gates. We usually use inverters to control the input. You also have like VDD at high and also VDD at low. So if you have the A as an input here, the Y will be generated based on your choice. The noise filtering, sometimes we use Schmidt trigger or high stresses changes where you will have lower VIH but it raises the VIL. Also, you need protection against electrostatic discharge, and we will see this soon. So we can use this circuit as well. So let's combine the input and the output both together with the bidirectional pads. So you have a pad here that will be connected using a gold bond wires to the lead frame all the way to the pin. So this pad here, it could be an output. You have some processing and it comes from the output as D out all the way and going from the D out to the pad. If you want to configure this pad as an output, you can configure it as input, meaning that it will be an input to the inside of the circuit. So it could be input or output. You need tri-state driver on the output, and you use enable signal to set the direction. You optimize the tri-state to avoid huge series transistor. So here in the enable, it tells you which direction you are going to use. Is it output or input? So let's say that you have the enable equals to 0. Here, if it is 0, then this AND will have a 0 value. So it's a 0 here, regardless of the value of the D out. And then this 0 will become the input of the, or after the inversion, it will be 1, which means that this is going to be off. Similarly, it will be 0 here, and this one will be 0. And since this is 0 as well, it will be off. So there is no batis coming from the output, meaning that it's going to be an input. Going to be input. Now, if the enable is 1, meaning that it depends on the value of the D out. So whatever D out, it will show up here. And the D out will, in turn, either the pull up will work or the pull down will work based on the value of the D out, and it will show up in the pad as a NOT. That's the way we're doing this. Now for this circuit to work, we actually can do it this way. You can see that this one is actually this one. And we have the NAND like this. We kind of do some sharing. So this is the NAND. This is static CMOS designed for the NAND, as we discussed. And here is the inverted input AND, which is a NOR. And this is the NOR here. You can see the parallel in the pull down. And this inverter is this one. Now, for the other side of the NAND, notice that we have a resistance. This resistor is very important to limit the current because you are actually connected to the outside world. So you have no idea how much current you are getting. So you need a current limiter, and you also need these diodes to do the voltage clamping, especially if you have ESD or the electrostatic discharge. So to protect against the electrostatic discharge, you have these voltage clamping, where if you have a spike, if you don't have this and you had a spike at the pad as the input, the spike maybe is too big. Let's say that this is the VDD level. And this is the spike. Usually it goes down to maybe throat. So it is this way. The spike goes up and down and so on, and then it's settled down. So if you have this spike without using the diodes, it will go inside after these two, and it might harm this inverter, the one that's first seen. So this big spikes could burn the thin oxide in the PMOS and the NMOS and destroy the circuit, and no longer you can input anything. So you use these actually to take out this, and it becomes like this, something a little bit tiny there, which will be no. So this is very important to protect against electrode discharge. Not only in VLSI design, in any electrical circuit. Now, to compile everything together, this is the MOSFET I/O pad, where it passes analog voltage directly in or out of the chip. So it's also do the analog. And you can see the idea is the same that we just discussed. This is from the output side, and you can select input or output from here. And this is if you want to do the input. You want to do the input. And the protection is here from the electrode discharge, and you have a resistance for the current limiter as well. So there is no buffering. Protection circuit must not distort the voltage. It's a 1.6 micrometer to metal process. We have protection resistors here. We have protection diodes against the discharge or the electrostatic discharge. We have guard rings. You also have a field oxide clamps here and there. To see the relation between this and this, this is the output. You can see it here. The enable, you can see it here. So the output goes this way and the enable goes this way. And you have the input, which is this in and input bar. You have the input and the input bar. This is the input and this is the input bar. Now you have rings, as we mentioned, the P plus guard ring and the N plus guard ring. So it's here and there, you can see it. All of these circuits need VDD. You can see the VDD and the ground. So the VDD, the ground will be here and the VDD will be here. And you can get them throughout all the circuits from this part. You also have a P plus guard ring again here. Now, for the output, from the output side. We have the output resistors here and there, PMOS and NMOS. And that's basically the things that we want to see here. Other than that, the field oxide clamps are here and there. It's an NMOS field oxide voltage clamps here and also here. And as you can see, the hole size here is 200 micrometer by 200 micrometer. And the first connection of the golden bond wire will touch this pad. Will touch this pad where it is 100 micrometer or into a 75 micrometer, and this gold wire will touch the pad, and from the pad you can go through this design, and after that you can connect it to whatever circuit you have. So your design will be below this, all the way below this. So your design will be somewhere here. And this is only a single pad. We should have multiple pads. Usually, for example, 8 or 28 pins and so on. There's many examples that as we speak to show you in the packaging. Now, if you have certain value in the design and you want it to be an output to the pad, you connect it this way. If you have something that you need to receive from the pad, you have the input and the input bar here. So it will be your input to your design. That's basically what we want to cover today. And this marks the end of this class.